Welcome to Live from Plato's Cave. I am Mario V. This is episode 23, How Science Works with Vincent Icke. Plato's allegory of the cave can be read as being about science. We're all watching shadows here in society, but somehow scientists are able to say something about the fire and the objects carried in front of it. They're able to imagine possible causes of what we encounter in our everyday life, the mechanisms behind what we see every day, and then find ways to put these imaginations, these hypotheses, to the test. But with science we have a similar problem as we discussed in the previous episode about education with Gert Bista. Because there's how science actually works and the conditions it needs to thrive. And then there's the idea of science that exists in society about how it works. And this idea, this picture of science, determines what role we give to science in society, including who gets to do science and who does not, which projects get funded, and what we demand of the scientists working on that research. For instance, demands of a clear question and predictable results. But it's kind of ironic that fund is the root of fundamental, but fundamental research is hardest to get funded. What if the way society envisions the scientific process is not how science actually works? Today I'm speaking with theoretical astrophysicist Vincent Icke. We've spoken twice before, in episode 7 on astrophysics and extralife, and episode 9 on the biggest question in physics. So if you want to know more about his work, listen to those episodes. In this episode, we'll speak more generally about how science works, and what kind of society would provide the optimal conditions for science to work. We discuss some of the topics from Vincent's latest book, which has been published in Dutch as Licht, Tussen waarheid en wetenschap, which can be translated as light between truth and science. In that book he writes, "How do we deal with the unknown? How do we increase our knowledge and our understanding? There are people who believe discoveries can be planned. They call this the scientific method. But usually it's actually a political method. According to the bureaucrats who claim to know how science works, that method consists of a 4-step cycle. Question, answer, publication, and application, and then the next question. In the Netherlands, this supposed cycle is the basis of government funding of scientific research. But that's not how science works." We recorded this conversation at Vincent's home on the 25th of October 2022, which happens to be during a partial solar eclipse in the Netherlands. Thank you for inviting me to your study this time.
Hi, good morning. A special day because it's a solar eclipse, so It's a very special occasion. Thank you very much.
Yeah, there's a partial eclipse in the Netherlands. How is that for you? Is that for you normal every day, or is there something special about it?
Well, scientifically speaking, there's absolutely nothing we can learn from solar eclipses these days. But I find that the emotional aspect of science shows very clearly in this case, because it is something that you can directly connect to. It really happens, So it's just like when you're looking at a dark sky, you see the planets or you see the moon, the direct connection with the universe is so wonderful in those circumstances. I mean, in my work in theoretical astrophysics, I'm always looking down, as it were, just looking at my papers, looking at my algebra, looking at my computations. But looking up at the night sky is something truly fantastic. And looking up at the day sky, like today when there is a solar eclipse, is also very nice. And so to try to imagine what this must have been 1,000 years ago, right, when people hardly understood anything about the way the universe works, how impressive it must have been. And still, with that frame of mind, it is still impressive today. It's just simply beautiful.
Yeah, I was speaking yesterday with a friend about, I don't know if this is from Kuifje from Tintin, but if a long time ago you did have some knowledge, you were able to predict a solar eclipse, you could wield quite some power, because
Yeah, there is Tintin has is 2 albums, and the second one, the Temple of the Sun. Tintin knows that there's going to be an eclipse, and he and Captain Haddock are going to be executed, and he asks it to be happening at the particular hour, and then all of the people who have captured him sort of suddenly think that he has supernatural powers because the sun hides itself, right? Which is really strange because Hergé, the writer of this Tintin story, framed this in the Inca Empire. And the Inca knew perfectly well that there's a regularity in eclipses, right? There's regularity in lunar eclipses, there's regularity in solar eclipses. The so-called Saros period, when certain types of eclipses repeat, was already known in those days. Except people didn't know the mechanics, right? Yeah. They just simply didn't know how the mechanics of the universe works. And that, of course, scientifically speaking, is fascinating. That you know all the regularities, but you do not have understanding of what this all means, what's all behind this. For instance, if you go back to Sumerian times, there are absolutely thousands upon thousands of clay tablets on which the astronomers in Mesopotamian times recorded the position of the planets and the phenomena in the sky and things like that. Very accurate, as far as the human eye could record things. But there was no knowledge of the workings of the universe. They had the data, but they didn't have the insight. They did not have the understanding. And that is a drastic difference between just simply recording things and amassing data and really understanding what the world is about. It used to be thought that science is about collecting facts, collecting data, right? Well, that is bull, because you can have libraries full of data, of exact observations that are really and truly facts. And those facts themselves don't tell you how it works. In order to go from facts to understanding, you have to invent something, you have to think of something, you have to frame a hypothesis. You have to think, you see these regularities in the solar eclipses and the lunar eclipses, and then you notice, isn't it remarkable that there's always an eclipse when the moon is not in the sky? This is quite interesting, right? It's not a matter of curiosity, it's a matter of attentiveness. You notice that whenever there is a solar eclipse, there is no moon. And then you make a jump. Okay, you invent something. You think, wouldn't it be possible that it is the moon itself that is a cause of these eclipses? And once you have that and you connect that with the fact that the moon progresses from night to night with respect to the background stars, from there you can think, well, maybe the moon is something that orbits around the Earth. Now it's absolutely stunning hypothesis, right? To first be the first person to imagine that there is this object which is actually revolving around the planets and every now and then gets in front of the sun. There's a monumental thing. There's a leap of understanding, right? You can amass data about eclipses until you look blue in the face, but the truth will never reveal itself out of itself. Right, you have to invent something, you have to hypothesize. Wouldn't it be possible that, etc., etc., etc.? You are confronted with data, you're confronted with a consequence of something, and you ask yourself, what is the cause of those phenomena? What is the cause of those consequences? What was the prior, as it were? And the data are not going to tell you. You have to think about it, you have to invent it. And somehow the human mind is capable of inventing these things, of thinking of, wouldn't it be possible that?
So the Aztecs were able to predict the solar eclipses? They were able to see the irregularities, patterns
Absolutely.
In the data?
Oh, yes.
But they did not understand the mechanics.
That's right. The very idea that there is such a thing as mechanics is an enormous innovation, right? In the old days, people called this the laws of nature. In my opinion, that is a misnomer. because there are no such things as immutable laws. A law of nature is a human invention that is intermediate between our human brain and the way the universe works. Which is not to say that the way the universe works is some sort of, opinion or whatever. It works the way it works. But we need a link between the universe and our brain. And that link we call a law of nature. But those laws change. I mean, the so-called laws of nature that we had in the 17th and the 18th century are drastically different from what we have today. Because we progress. We know that there is such a thing as mechanics, but we also know that there is such a thing as relativity. And maybe in 100 years, well, not maybe, but in my opinion, certainly in 100 years, the laws of nature we have now will have been embedded and extended by new understanding that we will have a century from now.
But then you say the laws of nature change, you don't say we have a more accurate picture of the laws of nature or a better understanding of the laws of nature.
I don't know about that. I mean, the way you phrase it, it sounds to me as if it's mostly a matter of language, so how you phrase this. I agree with what you said, right? The way in which we describe nature evolves and changes and adapts itself to new findings, to new computations, to new understanding. But you can see the laws of nature as sort of a successive approximation, right? But even that is not correct because it isn't as if, let's take again classical mechanics, right? It isn't as if we refine the theory of classical mechanics. We have classical mechanics and then we find out, like it happened in the late 19th century, that there is something special about the speed of light. The speed of light is invariant, it never changes. And therefore you have to modify mechanics, but it isn't as if you refine it, it becomes something really different. And then after that, we discover there is such a thing as quantum behavior. And you have quantum mechanics, but quantum mechanics is not a refinement of classical mechanics. It is a change. It is drastically different. And there are things in quantum mechanics that are just simply absolutely incompatible with classical mechanics, which for us, of course, makes it different to understand these things and to really intuit, as it were, to get an intuitive grasp of what is actually going on. So it isn't as if our understanding of nature is fluid in the sense that it could be anything, but it must be adapted to what we find in our observations, what we find in the laboratory, what we find in the universe, and that it's very difficult to describe. Yeah. You can try to say, for instance, well, it is like Darwinian evolution, right? Like Wallace and Darwin, sort of invented this idea. You have a lot of variation and then you select what works best and that will survive. To a certain extent, the improvement of our understanding of nature works that way. We invent lots of different hypotheses. Wouldn't it be this? Wouldn't it be that? Perhaps we have these particles. Perhaps we have that behavior of space and time. But then you compute the consequences, and the hypotheses that did not really reproduce the consequences will have to disappear or have to be modified or something. It is an analog of the way it works. But there again, it is not exactly the same. What does remain the same, however, is that in order to make progress, we have to have a variety. You see phenomena, and you have to have a variety of hypotheses of what this could possibly be behind this. What could the cause of these phenomena be? And then experiments and predictions and stuff will determine whether or not what you have invented, what you have thought of, is correct or not. And even correct is something that you have to take with a big grain of salt, because there is no such thing as correct. It is temporarily correct.
Yeah. correct seems like you have you can check. You have a picture and you have the reality, and you can check your picture against the reality.
Yeah, let me give an example. Right, even my dog knows that when we go out in the street and it rains, that rains and cloud go together. Mm-hmm. The dog knows that perfectly well. He looks up and he wants to go back home. Now, if rains and clouds go together, you can ask yourself as a scientist, what is behind this? What's the mechanism? And then you have to frame a hypothesis. And the hypothesis would be, in this particular case, if rain and cloud go together, maybe a cloud is made out of droplets, just like the droplets of the rain. And then somebody else comes by and says, look, that's completely illogical what you say, because if a cloud is made of drops, like rain, why doesn't the cloud fall down? Well, then you know from experience that very small drops get carried by the air streams, right? Because there's a lot of friction between the small drop and the air. So your hypothesis is refined, and you will say a cloud consists of very, very small droplets of water. Then you make a prediction. You say, if this is true, we should see a rainbow when there is a sun behind the clouds.
Yeah.
Because you see a rainbow when there is rain falling down. So if a cloud is also made of drops, you should see a rainbow when there's a sun behind the clouds. And lo and behold, this is true. Mm-hmm. The phenomenon is called the glory. That is sort of something that meteorologists call it, the glory. And you see the red and blue colors of the rainbow in the clouds. So that confirms your hypothesis. Does that mean that this hypothesis is necessarily always correct? No. Because then you can ask yourself, if this is true, where does the snow come from? Or hail? That is ice coming from the clouds. Maybe a cloud also contains ice in some way or another. That's another step. And you go on and on and on. So if you have a confirmation of your hypothesis, for instance, in this case, that if you have the sun behind the clouds, you can see rainbow phenomena, that doesn't mean that this is necessarily 100% always correct. It is only correct under certain circumstances, and it may be refined or extended in the future. So anything that you find, it is temporary. It doesn't mean it is wrong, but means that there is always room for improvement when your knowledge proceeds.
Is this the same what happened with Einstein's theory of relativity and the solar eclipse? I probably don't remember the story correctly, but there was a circumstance, a prediction of the theory that you would have to be able to see a star that was behind the sun, so you wouldn't be able to see it according to Newtonian mechanics. But you couldn't see that because the sun is too bright. So you need a solar eclipse to...
No, it's slightly more complicated than that. If it was already known in the 19th century that if you apply Newtonian mechanics to the motion of light, that light gets bent. Yeah. That's very simple. As light comes in with 300,000 kilometers a second, and when you shoot light past an object like the sun, you can compute. It's very simple to compute from Newtonian mechanics how much that light would be deflected by the gravity of the sun. Observing that is very difficult because the effect is very, very, very small. Gravity is quite weak. So you can only see this during a total solar eclipse, because then you can, as you said, right, the light from the sun is hidden by the moon that is in front. And then when you observe the position of stars next to the sun, and you can see that now because the main of the light of the sun is now blocked out, you will see that the position of the stars are shifted outward with respect to the disk of the sun due to the bending of the light rays. Now, when Einstein came with his general theory of relativity, that was not a theory of gravity. It is a theory of the structure of space. What we call gravity is a consequence of the curvature of space-time. Of course, we always use the word gravity. There's nothing wrong with that, because you can use for instance, you can say the sun sets, right? everybody knows that there's poppycock because the sun doesn't set, the earth rotates. But you can still say, well, I see a beautiful sunset and nobody will think that you're crazy. Similarly, you can use the word gravity, even though gravity doesn't exist. Gravity is a consequence of the curvature of space-time. Now, from Einstein's theory, it followed that this displacement of the stars during an eclipse should be exactly twice as large as what would be predicted by the Newtonian theory. And in, I think it was 1919, a total solar eclipse was observed specifically with the goal of finding out whether or not Einstein's prediction of this factor 2 was correct. And it turned out that it was correct. Right, so what was observed did not fit with classical Newtonian mechanics, but it did fit with general relativity. And what does this mean? It means from a physics point of view that Newton's idea, but there was actually Hooke also, I think, it was Robert Hooke also had this idea, that there is such a thing as a pull of gravity, a force of gravity. Newton's idea turned out to be wrong. And even in Newton's day, there was doubt as to whether or not this hypothesis was correct, because everybody was saying, well, most people were saying, look, if there's such a thing as a gravitational pull, where does that come from? There's no wire between the Earth and the Sun. Mm-hmm. And action at a distance, right, was suspect. But in any case, it worked. It worked beautifully well for the solar system. So, what was the worry? Einstein showed that there is no such thing as gravity, and therefore this whole problem of how could you possibly have action at a distance, this problem disappeared. It was solved. Poof, it was gone. And it was replaced by new physics, and the new physics in this case being that space and time are stuff. They are material stuff in a sense like, comparable with particles, comparable with bricks and mortar. Bricks and mortar are stuff that are material you can build a building with. And Einstein showed that space and time are also building material of a completely different nature than particles and cement and bricks and things, but it is still material with which you can make a construction. A construction in space can have a curvature, just like, for instance, the space of a surface of a sphere has a curved structure. And the consequence of that curvature is the bending of light and the bending of particles in space. The motion of particles is governed, in this case, by the curvature of space and time, and not by anything mysterious like an invisible wire between the sun and the planets. So I'm sort of expanding on this in order to show that this next step was not a refinement of classical mechanics. It was something drastically new. It was an extension in a direction that nobody before Einstein had ever dreamed of.
How would this be different if, let's say, we didn't have knowledge of Einstein's theory, but someone was observing the solar eclipse and they were making the same observation? Mm-hmm. And they were seeing, well, the I don't know how to say it, but what we observe doesn't fit Newton's theory. Mm-hmm. But they didn't have any, because on the basis of Einstein you could have two choices, or you have three choices. Either we observe what Newton's theory predicts, or we observe what Einstein's theory predicts, or it's somewhere in the middle, which I think happened with the Higgs boson a while ago, that they found something but it didn't confirm either theory. Mm-hmm. So how is it different when you wouldn't have this new? Does it matter that you have this new theory?
Oh yes, it does. But what you are proposing is what, in my view, would be a different hypothesis. Mm-hmm. So let us imagine, that there had not been this prediction by Einstein on the basis of his theory, but that observers, astronomers, had found that the position of the stars was different from what you would actually have expected. That's perfectly possible, right? And then the question, of course, is, well, curious, what could be the cause of this? And for the cause of this, you would have to frame a hypothesis. You have to come up with an explanation that is an invention that didn't exist before. And Einstein's explanation in this case would be the structure of space-time. But it's perfectly possible to have another hypothesis. For instance, do the following. Hooke and Newton proposed that gravity decreases proportionally to the square of the distance. If you make the distance between two objects twice as large, gravity between them gets 2 times 2 equals 4 times weaker, and 3 times further away, they have 9 times weaker gravity, and so on and so forth. Now, it is possible to explain this shift of the position of the stars during a solar eclipse by assuming that gravity does not obey exactly this 1 over r squared, we call this 1 over r squared behavior. That would be different. In other words, you would have to modify the Newtonian Hooke prescription for gravity. This has been done, in fact. There are certain motions in our universe, very large scale motions of galaxies, a motion inside galaxies, that require the presence of dark matter. Okay, so for instance, a galaxy like ours, or the Andromeda Nebula, or other galaxies, they rotate faster than you would think on the basis of the mass that we see is present in stars. So there must be more mass than the mass in stars. We call this dark matter, and in some cases there is a lot of it. Now, you can do either 2 things. You can say there is such a thing as dark matter, and we don't know what it is. Or you can say there is ordinary matter, but it does not behave according to ordinary gravity or to ordinary Einsteinian theory, but we need to modify this. This theory is called modified Newtonian dynamics, MOND, MOND people call it, and it makes predictions. Yeah. You can say, look, if the modified Newtonian dynamics is correct, then we should observe the motion of galaxies being such and such and la-di-da and a whole lot of other things that you can compute and compare with what actually is observed by the astronomers with their beautiful telescopes. So that's exactly what you just proposed a moment ago. You said, isn't it possible to come up with something else, namely a different theory of gravity? And the answer is yes, it has been done. I think this is symptomatic. It is not symptomatic, but this is sort of emblematic. This is typical for the way in which science works. You have, on the one hand, the hypothesis that space-time curvature does everything, and there is such a thing as dark matter. Or you can say, well, no, we need to modify things because the way in which space-time or gravity works is rather different. That's possible. Then you have to ask which of those 2 possibilities is actually correct. And in order to do that, you have to make a prediction. You have to sit down and compute and say, if theory A is correct, I should predict phenomenon A. And if theory B is correct, I should predict phenomenon B. Then we go to our observational colleagues with their telescopes and things and say, look, which of these 2 do you actually observe? And then there are basically 3 possibilities. Either A is found to be correct, or B is found to be correct, or both are found to be wrong. And if one of the 2 is found to be correct, you have to say, look, that particular theory, in this particular case, Einsteinian theory with dark matter, is for the time being the correct one. And then, of course, there's a new question that comes up and says, look, if it is true that Einsteinian theory is correct and there is such a thing as dark matter, what is that dark stuff? I personally don't use ever the word dark matter if I can avoid it, because the word matter already suggests that it is stuff that is comparable to your body or mine, or bricks or cement, or the surface of Earth or something like that, right?
You already make assumptions based on your current understanding.
Exactly.
While it might be something completely that we don't know yet.
That's right. That's right. So the MOND people with a modified Newtonian dynamics would say there isn't even such a thing as stuff. It is just the way in which the forces work. Yeah. Or you can say, like what I do, there is evidence for stuff, or the everyday parlances, you use the word dark matter. But you have, with words, you have to be exceedingly careful. Since we're still on the astronomy tack, let's consider the word Big Bang, right? It was invented by Fred Hoyle to make this idea ridiculous. We now know that this is correct, but the word Big Bang suggests that there is an existing empty space, and at one particular point, at one particular time, there's a giant explosion in space. Yeah. This is drastically wrong. That is totally not the way it happens. But the word Big Bang then sort of, gives you such a completely wrong impression that you start asking the wrong questions, like what was there before the Big Bang? This is an impossible question. In algebra, if you write it down in formulae and in equations and stuff,
you don't
have this problem. Yeah. And that is, of course, because our friends, the mathematicians, have been so clever as to define things in such a way that there can be no two meanings for the same concept.
Yeah.
But in ordinary language, the language that you and I use during this podcast, in ordinary language, this is not mathematics. So a given word, like understanding or experiment or fact, all those words we use in language are somewhat fluid. They're a little bit vague, which of course is very useful. I mean, you and I could not communicate, and we as humans could not communicate with one another. Yeah. If our language were not pliable, it would not be adaptable.
No, then you could only communicate if you exactly understand the same thing. But in our language, it's actually good that we have some space. We think we mean more or less the same thing, or we're pointing at more or less the same area.
Exactly. This is, of course, the most noticeable in adjectives. When I say a sunset is beautiful, I use the word beautiful as an adjective, but for you and other persons and stuff, the meaning of this would be drastically different when you try to compare it, right?
Yeah.
But even so, you and I can agree on things that we find beautiful. And we go to a museum and you say, I find that it was a beautiful painting. And I say, well, it wasn't really made for me. And then I see another painting and I say, I find that beautiful. And you say, well, it wasn't really made for me. And then there will be some paintings in the museum that you and I agree on. Yeah, that's really beautiful. Mm-hmm. And still, our mental concept of beautiful for you and me will never ever be the same. Yeah. And we can talk about it. We can both enjoy this museum. But, that would all be impossible if the word beautiful had precisely and exactly only one meaning. We could never communicate about stuff like this, right? And similarly about seemingly ordinary things. It's only you use a word. We have a dog in the house here, right? Well, there's a dog, but that's not one particular animal.
Yeah.
Right? Is it a small dog? Is it a big dog? Is it this breed? Is it that breed? Is it old? Is it young? Blah, 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 blah. The vagueness of words are a blessing in language, but they are a curse in the description of nature. Mm-hmm. And that is why we use mathematics.
Yeah. I really like this direction because, we can kind of go three ways with this. One is that Charles Sanders Peirce, a philosopher, said that if this weren't the case, we would never invent something new, because it relates to what you say about hypothesis and imagination, because you could only speak about everything that you already know for 100% sure. So if this idea of science that you just have to observe the data and then by induction you get an understanding, but that can't happen like that, because you can see patterns, but you don't have in order to have a hypothesis about the mechanism, you need this new step. And the other way is by deduction, is you can make predictions, but you can only make predictions on the basis of what you already know 100% certain. So it would be maybe we would have less misunderstandings in society, but we wouldn't have any innovation or evolution, I think. So, and there's two other directions. One is I want to talk to you about grants and grant proposals and what is, because in the grants you have to say, I'm going to make a groundbreaking discovery. Anyway, we speak about this later. First, more like, I guess, philosophy of science question, because what you've said so far is based on theories. So they are acts of the imagination. But as you write in your book as well, we are also kind of anchored in the universe, because you have to make these predictions and you have to check if, this actually happens. But what if there's a theory that is actually, if you can look from a God's eye perspective, which I don't know if it's possible, you can say, well, this is actually how it works. But that theory doesn't make any predictions that we can verify. So it could be, or maybe it could be someone just in a room thinking this up and thinking, wow, this is how it works. I think it kind of works like that with string theory, where you have this whole mechanism, but you can't really make a prediction on it. And on the other side, you have this kind of, you compare it to a dentist, you make predictions and you adapt it. So you're kind of working your way through this path. But if it were the case that this other theory were more correct, but you don't have predictions, then we have a problem.
In my opinion, any description of nature that is incapable of making verifiable predictions does not count in science, at least in the physical sciences, right? In the little book I wrote about it, this is in Dutch, it is called Licht, Tussen, waarheid en wetenschap, light in between truth and science. I do claim that in order to qualify as a scientific explanation, as a scientific theory, one must of necessity make testable predictions. Because otherwise, there is no way in which you can discern between various theories or various descriptions, right? And I think in society, people already realize that this is the case. That there are important things for humanity for which a test does not exist. There is no such thing as a test as to whether a particular religion is right or wrong. There is no such thing as a test as to whether a particular poem or a particular painting or a particular piece of music is right or wrong. Those are untestable things, and still they are important to us as humans. So in this respect, I think that the physical sciences stand apart from other things that humans do, because we have incorporated the test as an essential part of our procedure. And you can only test things when there are predictions, right? You sort of, when my theory about the motion of the moon around the Earth and the motion of Earth around the sun, when my theory is correct, I predict that in the year 2026, on August the 8th, there is going to be a solar eclipse visible in the Netherlands that will cover 88% of the surface of the sun. That is a prediction that I make right now while this solar eclipse outside the house where we're sitting is taking place. I also predict that the eclipse will be total, where the moon will be completely covering the sun, to be seen from the north of Spain. So if you happen to be in Spain and having a holiday in the beginning of August 2026, I predict that you will see a total solar eclipse. And that is based on a mechanical description of the solar system. Now, you can come up with something else, but unless there is a testability that you can actually go to the north of Spain and verify whether or not on the 8th of August 2026 there is going to be a total solar eclipse, you can say anything you jolly well please. And therefore, there is grounds for disagreement, but that disagreement is insoluble if there is not such a thing as a test. when one particular religion says that this religion is true and another drastically different religion says that this religion is true, there is no observation, there is no test, there is no experiment that can say whether or not one or the other or both are wrong. And of course, we know that in human society, that is a great cause for conflict. Leibniz, a great scientist and mathematician, said in one of his writings that he hoped that at some time in the future we would understand the workings of the universe so well, including the workings of our mind and the workings of our psyche, of our soul, as it were, that a quote, it's a vague quote from Leibniz. I'm not really certain if this is literally correct, but the quote goes approximately as follows, right? If in the future there would be two philosophers who differ in opinion, they would sit down at the table, look at each other, possibly in a friendly way, and say, let us compute. Mm-hmm. Right? Now, of course, that hasn't happened. Leibniz did never see this coming true, and we never will, because there are many things in human society that you simply do not allow a test. But without a test, there is no such thing as physical science, and that is basically my response to your hypothesis.
Yeah.
You have to be predicting things. You have to be something that is testable.
But it could be that I think that Leibniz in his time, he had a kind of understanding. He was also a philosopher. He had kind of understanding that maybe more in line with quantum mechanics. And well, at the time he was living in where the atomistic and the Newtonian worldview was dominant. Mm-hmm. So in his time, we could say maybe that he would have been more right about certain things than his contemporaries, but he wasn't able. The technology didn't exist. Maybe some other things didn't exist. He wasn't able to make predictions yet, but still, he could be more right in that circumstance. And so my point is not. My point is more about maybe the role of luck as well. That what if the solar system was formed in a slightly different way, that the moon didn't pass in front of the sun or the other way around? Then we wouldn't have those solar eclipses that
is
could
correct.
teach us something.
No, absolutely. In that case, we would just simply be stuck with the motion of the planets. Right?
Yeah.
But Hipparchus from Samos, it was 300 years BC, already had a mechanical model of the solar system that basically is the model we have today. It is usually attributed to Copernicus, but Copernicus was, it's something like 1,000 years too late or something thereabouts. It doesn't really matter.
Yeah.
When you go back to Leibniz's optimism of being able to settle philosophical arguments by just simply computing, you have to go back to his days, right, when the successes, the quantitative, computable successes of Newtonian mechanics were absolutely overwhelming, right? It's just fantastically beautiful that the tides and the motions of the planets and the motions of the stars, la-di-da, just you name it, right? That all seemed to fit this wonderful mechanical theory of Newtonian mechanics. And from that to have the what shall I say, the feeling, the hope that conflicts would be something of the past because we understand nature so well, right? That was, even in those days, very, very oversimplified.
Yeah.
If Leibniz would have just walked out into his garden and would have been asked the question, look, you see the flowers growing there and you see the mice sort of making little burrows and stuff in the earth and stuff. How do animals work? How do the plants grow and stuff? You give me the theory that describes the growth of a rose.
Yeah.
He would have been not been able to say, okay, that works in such and such a way. However, there was the hope that someday in the future we would discover the forces, the laws that govern the growth of a rose and the walking of the running of a mouse or something. What I find remarkable is that even in those days there were phenomena of which it was perfectly clear that they could not be explained, even in principle, by Newtonian mechanics. Mm-hmm. And one case in point is the diffraction of light. Okay, if you have light that follows a path in space, and you let that light make a shadow from a very sharp edge. You take a razor blade, right? There's a very sharp edge. And when you look at the shadow of a razor blade, and you look extremely carefully, you see that that shadow is not sharp. The shadow is a little bit wavy. Okay, there's a little bit more light and a bit less. It's sort of like a little ripple, as it were, on the side. That was already observed in those days. There is absolutely no way that Newtonian mechanics can explain that. We know now why this is. That is because light has wave properties. Yeah. Light is a wave, and waves can make interference, and interference will make these diffraction patterns and stuff. So if Leibniz and his colleagues had been sufficiently attentive, not curious, but attentive, just simply seeing things that are drastically different, they might even have picked that up. But it doesn't really matter. They were brilliant people, right? I'm not really dumping on them. But it took, until 1926, until Schrödinger came up with this Schrödinger equation that describes precisely how this happens in the wave particles, in the wave light, and so on and so forth. Yeah. Okay, and as already mentioned in the beginning of our conversation today, if you come back 100 years from now, I really want to live that long. I won't, but just simply just jumping 100 years in the future and seeing the ways in which our current understanding of the universe have improved in directions that we cannot even conceive of today, that would be just fantastic.
That for me is really emblematic for science, that you're not just, I'm hoping that the predictions that I made will be right, but that there are probably things that maybe even things we're looking at right now that, it was there all along. The data was there all along. We just didn't see it.
Yeah.
So I love speaking about science in this way and thinking about it and thinking about the past and also thinking about how science, the way it works, is very connected to the society that it takes place in. And in the last episode, I spoke with Gert Biesta, who's a philosopher of education. And in his book, World-Centered Education, he asked this question, because you can have the question, what kind of school does the society need? So, and then you usually get the answer of, we need to teach mathematics and this and this and this to prepare people for functioning in society. But he asked the question, what kind of society does the school need? So if you disregard all the useful functions of school, and in this case, I want to speak about science, of course, science can do a lot of good for us, but if you just think of what you explained as the scientific process and the way science works, what would be the ideal situation or this ideal society?
Whoa.
Okay, so to narrow it down, how
yes.
What? Okay, let's say I give you a magic wand and you could change some things about the Netherlands in the way grants are awarded and the way science is done. What would you change?
Well, that's a very funny question. Let's for the moment, if you allow me, let's take a little distance from granting things, money and stuff like that. The money is important, but let's sort of do it in two steps, right? One is sort of the general, the non-measurable behavior of society, and not money, but the attitudes, as it were.
Yeah.
In order to say things about that, what I would like to do is sort of go through the steps that, at least in my case, the physical sciences work. Okay, that you start with an observation, right? Clouds and rain go together. You notice something special about that. You have to be attentive. about something that is remarkable, right? So the going together of these two is what you remark upon. Then the next step is make a hypothesis. The hypothesis is clouds are made of droplets. Then the next step is a prediction. You predict that if clouds are made out of small droplets, when the sun is behind the cloud, you should see a rainbow effect in the cloud. And then you go and you make a new observation, not the observation you had already, because that's easy. But you have a new observation that determines whether or not the prediction is correct. And if the prediction is correct, your hypothesis has, for the time being, been verified. Now, let us see which of those steps relates to society. Okay, the first step, observing, is something for which you need observational instruments these days. I mean, ever since the 16th, 17th centuries, we know that the physical sciences, our human senses of hearing and seeing and stuff like that are not adequate. So you need instruments. Therefore, you need to have a society that is technologically sufficiently advanced, as it was, for instance, in the 17th century when people started to build telescopes. You also, in most cases, need patience. You need to have the leisure to collect your data. And that of necessity means that your society has to be sufficiently rich, sufficiently wealthy, sufficiently well organized, that you have the time to do observations over a long time. There's not just simply for us, right? I already referred to the fact that in Mesopotamian times, people wrote down the positions of the planets and the stars on clay tablets. Well, even the observers in those days needed time, leisure, in order to do this. Most of them would have been priests or something, I don't know, but you need the time, you need a stable society for that. Then the next one is you have to notice something. You have to be, observant. You have to say, well, wouldn't it be peculiar that? That requires in society that those individuals that have that capacity, that are attentive, that see what other people do not see, that those individuals are permitted to do that, which means that society has to be permissive. You have to allow people to do these things, right? You do not have a robot society, but you have to be permissive, as it were, to a certain extent.
But what does that mean concretely, being permissive?
Well, let me take my own example. I'm a professor of astrophysics, which means that my society, the Netherlands, Europe, have given me the liberty to do that. That is permissive. There is nobody that stands behind my desk and behind my books and my computer and stuff saying, no, Vincent, you cannot do this. You must start doing something else, whatever. No, I am, as it were, an emissary. I've been allowed by my society to do this. Mm-hmm. And let me make no mistake about this. I'm very grateful for this. And not only I myself, but my colleagues also who do science have to be permitted to do it. Yeah. All right. So
you're a professor, but you also know I don't know how it is in your field, but in my field, you have the postdocs that have contracts for 1 year or 2 years, and they're very dependent on. Sorry, I'm already going to the practical situation.
There is a certain career progression. Yeah. Right. But even students who started, for instance, you start to study astronomy. Mm-hmm. In my particular case, I studied theoretical physics, I studied astronomy. I have to be permitted to do that. My parents, straight after the Second World War, did not originally think this was a very good idea, because they thought that it would be better if I started to study medicine. Yeah. But becoming a medical doctor, you are immediately useful to humanity. Whereas if you're an astrophysicist, this is not so clear. Right. But I was permitted by my parents and by my society to follow a career in theoretical astrophysics. That is, and that was true when I was a student. That was true when I was a graduate student and wrote a PhD thesis. And that was true through the rest of my career. And that also holds for other people working in this field, right? We are allowed to do this. And that not everybody becomes a professor is purely a matter of, numbers. I mean, everybody who graduates in astronomy could not possibly become a professor, because all of a sudden the university will have 200 million employees. There's no such thing, right?
No, I also mean in terms of you are allowed to spend time on it, but let's say the lower you are, maybe as a student is also an ideal situation. But if you go further, you have to write a project proposal. And this project proposal has to be approved by many other people.
But look, no, I'm sorry. What the financial and personnel consequences of this are, let's postpone these for a moment.
Okay, yeah,
because I'm really thinking for the moment more about the cultural and abstract properties of society.
Okay, yeah.
And the fact that society allows people to do certain things like this is extremely subtle and important. I mean, if I were to be a scientist in China, which is an absolutely totalitarian rogue state with cameras all over the place and people recording even if I go to the toilet, okay, you do not have the liberty. You are not allowed by society to do things the way you think best. Yeah. There is some kind of communist party that has determined what is best, and your opinion does not count, is not being asked for. So that liberty, that freedom, is something which is absolutely essential for science, I think. Then the next step, framing a hypothesis, again, is something that relates to a person. Some people are good at it, some people are not so good at it, right? If you're not so good at it, then you will never become a scientist in this particular case. That doesn't really mean in any way at all that you are less important than any other human person. I mean, all people have the same rights, but you're just simply not sufficiently suited for this. Mm-hmm. You know, I'm not a sports star because I cannot run fast enough. This doesn't mean I'm any less than anybody else, except I don't run so fast. So the ability to frame good hypotheses is something that some people have and other people don't. And we do not know why this is, but society permits the people who do have this property to proceed. Just like society permits people who are exceedingly good at other things, like artists or bricklayers, I don't know what, right? I mean, if I have my water mains installed here, I don't want to have leakage anywhere, so I need people who have talent for doing these things.
Yeah.
They're valuable. Anyway, so the next step, making a prediction, usually requires instrumentation. Computers, libraries to look at the right equations, conferences in order to talk with people about other experiments and so on and so forth. So that is a certain amount of, what shall I say, infrastructure. You have to have institutes. You have to have
people to help you and support you.
Precisely.
Yeah.
So that makes an appeal on the collaborative structure of society. We humans, we are group animals. Mm-hmm. We're not like a tiger who is an individual. We're monkeys. Okay? We're group people. And the group behavior at that particular step is important. You should cherish it. So you should have conferences, you have lecture series, you have colleagues to talk with, etc., etc., etc.
Yeah, which is also an environment where people can imagine and form hypotheses.
Yeah. And again, and it's good that you say that, because there again, that refers to what I said earlier, that a certain amount of permissiveness, a certain amount of liberty, a certain way of allowing people to do, I sometimes call it thinking crazy thoughts. Mm-hmm. I am permitted by my society to think crazy thoughts, and then to verify whether those thoughts happen to be correct in our universe. And then the final step, when you observe and try to find out whether a prediction is correct or not correct, requires material investment. We have telescopes. Okay, the space telescope costs 1 billion euros. Yeah. That is serious money. And we can build these things because all of society, in this particular case Europe, okay, spends a very small fraction of their gross national product, something like a fraction of a percent, on doing these experiments. And the percentage is small, but that doesn't really matter. What matters is the sentiment behind it. The fact that it is spent at all, the fact that my society spends the money of everybody on building a new telescope to look at the behavior of the universe and to verify whether our theories are correct or not, that is a generosity of our society. So permissiveness of society for people to do bizarre things like astrophysics, and the generosity of society to spend a small fraction of the gross national product on science. That is what you need. So and also that of course necessarily means, in order to answer your question, what sort of society would you require? The society must be relatively stable and relatively prosperous, relatively wealthy. Because if we are all starving, if we were all starving, I would not dream of asking for a new telescope. No way. But we're not starving, we're prosperous, we're doing reasonably well, and so on and so forth. Of course, there are other requirements, but that's it. And now sort of finally come to your original point. If you are prosperous, even if you're prosperous, you cannot spend an infinite amount of money on science, of course. Mm-hmm. And from then on, it is a matter of societal consensus. So the final link, in the final step in this whole argument, is that you need society in which societal discussions can take place in a more or less peaceful way. In other words, we need a government that is reasonably stable, that is not dictatorial, but that is, at least in my opinion, is democratic. Yeah. Because if I'm going to spend everybody's money on a university or on a new observational instrument or on a new library or something, I'm going to spend everybody's money, I will jolly well have to ask everybody whether or not they agree with this. And I cannot very well go and ask every of the 17.5 million people in the Netherlands, do you please agree that we build a new library for my university? You can't do that. We have representation of government for this. And that is why I absolutely adore democracy in this case. We indirectly ask the people of Europe, could we please build another library or another telescope or whatever? And that is the kind of society that we require. Mm-hmm. Now, how much money we spend on this is something for the various governments, for the European government and for the national governments to determine. If they say it is going to be so and so and so much, because we have other requirements, we have to do something about the global warming, we have to do something about global education, etc., etc. I say, okay, fine, fair enough. Our representatives, our government, have determined that no more than this will go to science. Yeah. And will gratefully accept it. Now, how precisely you divide that money is something that will always be a matter of struggle, right? What I do oppose is the current trend that promises must be made about the results of our research. You can never, under any circumstances, honestly promise anything in academic work, in science. Yeah. You just simply cannot. If I say, I'm going to do this and this research and the outcome is going to be such and such, I don't have to do the research because I know the outcome already. If I promise you an application of my scientific findings, that is bosh, that is just complete gobbledygook. No way can I promise anything at all. The only thing you can honestly promise is that you will do your best. You will do your best in gratitude to your society. And I don't mean this in a slimy way or something. I am deeply and truly grateful for having money for science. Yeah. And I will definitely do my best to use that liberty in a responsible way. But that's all I can promise.
So, because I don't know if I ever told you, but a big part of my job is writing grant proposals, but for the social sciences, for medical education. So there are some grants that they call them high risk, high gain. Mm-hmm. So it's not quite what you say, because you don't have to promise I'm going to. But if you write a grant proposal, one of the parts is a list of deliverables. And another part is a list of, if my research succeeds, or actually you shouldn't say that, you should say, I'm confident my research is going to succeed. And when it succeeds, this will be the outcome. So do you think that this part of this box of the outcome of the deliverables, is that a good thing? Or?
No, that is definitely wrong. That is
but
100%
that is
bad.
one of the most important things about that decides whether you get the grant or not.
I know that.
Yeah.
But this is based on the misconception that in the sciences we're answering questions. We do not.
Mm-hmm.
If I can formulate a clear question, I already have 75% of the answer.
Yeah.
That's not research. Let me give you an example, right? We were talking earlier about Einsteinian theory, about the structure of space-time and all that, and the curvature of the path of light when it passes by the sun. Let us look at what this really means in terms of physics. In Einsteinian theory, the matter, the stuff that you and I are made of, and the sun and the earth and the planets and stuff, curves space-time. And in curved space-time, things follow curved paths. The curvature of the planets, the orbit of the planets, the curvature of light, etc., etc. Now you can ask yourself a very simple question. How does matter manage to curve space-time? That's a question that fits not just simply on the back of an envelope, but that question fits on the back of a postage stamp. In terms of physics, this is a sensible question. And maybe it makes no sense at all. Mm-hmm. Maybe I was talking about what happens 100 years from now. If I were to come back 100 years from now, then quite likely this question will turn out to be silly. Right? So, well, you maybe in the year 2022 you thought this was a sensible question, but it turned out to be completely beside the point. Yeah. Right? Asking a question is not really what it is all about. And that is why I cannot even I cannot even formulate a deliverable. That I cannot promise a deliverable, okay, we'll agree upon. But I cannot even formulate it. So I write a research proposal. What I want to do, and I'm not going to voluntarily step into my grave until I have found out how matter curves space-time. Yeah. I really want to know this.
And this is understanding.
I'm desperately serious about this. This is something that I truly and seriously want to know. Yeah. My research proposal would only have to consist of that question. But that is silly. Mm-hmm. There is just simply totally no way that a deliverable can be derived from this. I can say, well, I sincerely hope, and I will do my best, to find the answer to this question. Well, I said, okay, give me the money because I formulated the question and I formulated a hope that I will be able to answer it. Yeah. That's all I can do.
I agree with what you say, but this is not how the current system is set up.
I agree with that, and that is why I disagree with the way the system is set up.
So what are we going to do about that, or what could be done about it?
I don't know.
Okay.
What I do know is that the formalistic way of saying that what we need is we need to start with a research question and deliverables and so on and so forth, that this does not match the way in which science actually works. Mm-hmm. Right? One can try to be cynical about this. And I have worked for almost 8 years in the United States, and in there the situation is even worse than here. And I know that many of my colleagues were cynical about this to the extent that they just wrote research proposals according to the rules that the government had set for them.
Yeah, it's a whole art. Like, okay, you want to do this research? Now
Exactly. But they knew perfectly well that this was a scam.
Yeah.
Except they said, look, we'll just simply make believe. And by the time we publish our papers, all we're going to say is like, we did this and did that and the other. And what they then do is that if they find results that do not actually fit in the original research proposal, they use this as an advantage, saying, "Oh, we had a
even more than what we promised."
This is a serendipitous word for this. A serendipitous discovery, etc., etc., etc. Great, la-di-da-di-da. And they make the headlines in the New York Times and so on and so forth. That's a cynical attitude, right? I do not agree with that. Being cynical should not be the appropriate attitude of a scientist. But I don't know what to do instead. All I can think of is go back to what we said, maybe 10 minutes ago, that to impress on policymakers that what we need is a permissive society, a society that says, look, we'll give you a very small percentage of our gross national product to do science with. We trust that you'll do this well, and just go and run with it. And then you can say, okay, who will then take care that this money is spent in the right way? And I have an answer to that. The answer is that we will. Because there is such a thing as competition in the sciences. I absolutely want to know how mass curves space-time. But a colleague of mine in Munich or in I don't know where will have a similar question. And we're both working independently on this, but there is a competition there. We're not enemies, we're colleagues, but we're still competitors. And as long as there is competition, where different people use their liberties to follow different paths, there is enough tension, there is enough strength in the whole field to make certain that the money is going to be spent more or less correctly. Nobody in my trade who is given a billion euros would build an instrument to observe bullshit when there is so much competition that we will almost always spend this money in the right way, not because we follow the dotted lines that the apparatchiks set for us, but because we love our science, because we want to progress, we want to get ahead, we want to get results, not because the results are on the dotted line, but because those results are what we live for, and what I live for, what my colleagues live for, and that tension, that strength, I think will guarantee almost to society that we will not just simply waste their money, but we will do something good with it.
Thank you so much for speaking to me again.
Thanks for the invitation.
Thank you for listening. And speaking of funding, this is an independent educational podcast. I could really use your support to keep it going. Visit livefromplatoscave.com for ways to do that.